Okay, good afternoon, ladies and gentlemen. So let's start the afternoon session on time. So my name is Regina Dittmann. I'm from the Forschungszentrum Jülich, and I'm very happy to announce the first speaker of the session, which will be Paul Lukowicz from Kaiserslautern University, and he will talk about leveraging foundational models for multimodal perception and situation awareness. So please, the stage is yours.
Yeah, thank you very much. Okay, they need to switch the, yeah. So I guess the talk is slightly more removed from just the neuromorphic part, and I guess the obligatory foundational model Gen AI talk have at every AI conference. But it's not that far from special hardware, because I'll be talking about using those models to advance sensor-based perception. And first of all, thanks to some people from my group who've been involved in what I have been talking about. And just acknowledgement to our sponsors. So this is mostly part of the Humane AINet project, a huge part of a huge cluster of AI on demand and AI Network of Excellence European projects. And the focus on the project, where it comes from, is really on building AI systems that try to enhance human capabilities. And as a result, in terms of questions that we address, it's really building common ground and shared representations between AI and humans. And from that, of course, we come to the question, how can you build those systems that can develop sophisticated models of situations in the real world? And then, of course, as nearly in every area of AI, you come to generative AI and foundational models. And foundational models, and as they are called generative AI, mostly make the splash in public by things they generate, like videos, music, fake, whatever. But the argument I'm trying to make, that these are actually just applications. The real fundamental significance of those models is that they are noisy, probabilistic, but extremely comprehensive world models, right? I know people debate that. Well, I'm one of those people who very strongly argues that these models cannot reason, they don't really retrieve any knowledge, right? They're just probabilistic models of distributions of lexical tokens. But because they're trained on texts that people use to describe reality, this probabilistic distribution corresponds to a probabilistic, extremely elaborate world model. And the second thing that is really relevant is that that world model is represented through those embeddings, essentially representing all our reality, our complex world, by a several hundred-dimensional vector, which is actually quite fascinating, which means that you can easily couple different other applications and modalities to that world model. And the way I like to think about those models is not as much how can I teach that model to do A or B, but rather how can I leverage the fact that I have a noisy but extremely comprehensive world model to implement this or this AI application. And in my research, what I look at is actual perception and situational awareness. So how can I leverage these world models? Now, if you look at visual perception, I don't know who of you played with those models, but what I did, just for the fun of it, I took those pictures, random pictures from the web, and fed them to GPT-4 and asked it, what does it show? And actually, it's amazing, right? I've been working in this notion of perception, of situational awareness for the last 25 years, and things we were trying to figure out before, what you now get from the model, right? You don't only get a nuanced description of the activity. It's not just planks, but planks with a dumbbell, and it's not push-ups, but mountain climber. But the system puts it in context of a larger scene, right? What are these exercises for? What is the scene? So when it comes to visual perception, these models already essentially solve a huge amount of questions. So what is the point? Well, what I would like to talk about is that beyond such capabilities, there are two interesting questions. One is, go from just perception to situational awareness, and then there's going beyond vision. So let me just first talk about this perception. And that's something, when I, 25 years ago, went into ubiquitous computing, the question that the community was working on is, take a mobile phone, add to the phone a couple of sensors, can you teach the phone where to ring and when not to ring? Now, interesting thing is, 25 years later, it remains an unsolved problem, right? You can do the simple things, like have your phone recognize that I'm in a talk, but it doesn't really solve the problem, right? If you're in a meeting and you want to know whether to phone ring or not to ring, it depends on the dynamics of the meeting. It depends of who you are, who the other people are, who is calling, right? If I had a fight with my wife before I went to the meeting, I may actually want to take the call no matter what, right? So it's not just the perception of recognizing the meeting, it is this awareness of the entire complexity of the situation. And I would say a couple of years ago, you would say, no, there's no way I can actually teach a computer to do that. And here is a slide. I used to show you my AI lectures, right? Showing what AI can do and telling people, voice recognition works perfectly, but something subtle like this, the system will recognize, right? So you have a waiter, he comes with a salad and a meat, and who says the salad, who has the meat? And the lady says, I'm the rabbit, right? Of course, we all know what it is. We all have all connotation of this thing maybe not being quite politically correct and not appropriate in every situation. But my statement was that it's something that's not going to work. So what I did just yesterday when doing the talk, I essentially inputted exactly this into GPT-4, and you get a perfect answer. It's still not perfect because many of the most subtle things it doesn't recognize, but it's quite amazing how it can leverage the world model it has to provide this answer. But of course, that still is not yet all that you have to situational awareness, right? Because what you need to do is, this thing is just a model, so you need to do two things. First of all, giving a situation, you need to understand how to query the model, right? There's all this thing about interface between perception and LLM, all this query engineering. It's maybe not that interesting in that quorum, but of course the other thing is, if you want to have such a comprehensive model of the situation, you have to go beyond vision, right? It's not just a picture that you have, it's all the sensors, my personal state, it's the sound, it's many other sources of information. And the question is, how do those sources of information relate? How can I use them to query the model to get those answers, right? So there's this issue of this, there's more to perception than vision. And it's really amazing to see what today the distance is between what vision can do with the models and what sensing can do. Right? The previous example was commercial system, GPT. So here's a commercial system for using sensors to recognize activity, right? The smartwatch with fitness recognition. Now, what the watch can recognize is essentially 5 different broad categories of activities, right? Not interpret an arbitrary scene and describe it. And you have a very similar thing. You look at the other commercial thing, Android activity interface. You have, I think, 7 or 8 classes of very simple things that you can recognize. Right? So the difference between what now you can do with vision using these models and what you can actually do with other sensing modalities remains huge. So what is the reason? It's very clear. As I said, on the vision side, you essentially map your visual input into this comprehensive dense vector space represented world model, whereas today the sensor application remain vertically trained, dedicated things. So why is that, right? That was just stating the obvious. And if you look at it, there are essentially 3 differences and 3 issues with using the power of those models for multimodal perception. The first one is the input space diversity. The second one is lack of the synchronized data sets between language or vision and the sensors. And the third, less obvious, is the nature of the information. So let me talk about this a bit. Now, the first one, yes, images can come in all forms and sizes. But at the end of the day, the information in every image is very much the same, right? You look at structures, you look at objects, you look at distances, you can reduce and compress the resolution. So it's pretty homogeneous. You look at sensors, right? You can have even IMUs at different body location. You can have impedance sensor, capacitive sensors, all sort of sensors. They're vastly different, and they cannot be easily put on the same level, right? So training this sort of general sensor model is not that easy because you're talking about very different things. If you look at the availability of data, there are actually some of those models. You may know them. CLIP is the most famous, or one of the first vision language models. They trained a version where they aligned this embedding space with IMU. The point is, all they did, as opposed to the 500 million image caption parts they use for vision, they mounted a GoPro on somebody's head, recorded a couple of hundred of hours of video with a single sensor, and used this to match it, right? So the amount of alignment that you get between the sensor data and the knowledge in the system is just very small. You can use it for very, very narrow things. There's another system recently emerged that it's called ImagePoint, where they actually go a more interesting way. They say that the anchor modality is not speech, but it's not language, but it's vision. And again, they code-train various, they say, sensors. But you see, 90% of the sensors are things that are just versions of vision, right? They mention IMU, which is essentially acceleration motion sensors, as one of the things for which they have 800 hours of data. Right? So there really exists nearly no jointly recorded data. Now we come to the third problem, which is sort of less obvious. Now, if you look at the way those things work, right, the foundational vision models, usually they will take a text, say, describing those two activities, screw driving and hammering. You can compute textual similarity, you can compute similarity between the images, and somehow you map it into this space. And you see that both in text and in image, those two scenes have a lot of similarity. Makes sense, like screw driving, hammering, all come into building things, all come into fixing things. They should be similar. Now, if you look at the sensor signals, then the sensor signals, and that's just a motion signal, right? It's accelerometer and gyro. The signal difference between the two is huge, right? Because if one is turning, the other is hitting. So these signals have very, very little in common, very, very little to each other. So if you do similarity, you don't get much similarity, right? If you force them to be similar because of the other embedding, you're likely to actually destroy information in that signal. Why is that? Essentially, it's pretty simple. The information encoded in the image is about presence of objects. It's about the relationship between the objects. And that's the same information that you eventually also have in the text. And the reason we have it, of course, is that we humans invented language to describe the world as we see it visually, right? That is why aligning visual and text representation is not that difficult. Whereas sensors are actually about physical properties of the systems, right? So they have a very different type of information that is encoded there. And that is why it's not that easy to actually align these forms of information. So what can we do about this? Now, the first thing that is pretty obvious, where people now work a lot is using essentially video to generate synthetic sensor data, right? So you can have a person, you recall the small data set of a person where you have videos, and you also have some sort of a sensor data, and then you go and generate poses from it, and you train a network to map videos onto this simulated sensor data. Because the video information contains a lot of information that you can use to reconstruct sensor data, and once you have done that, you can essentially use this encoder to just crawl the web for sensor data, for video data, which also has image captions, then mapping that to generate synthetic sensor data, and then to using these to train an aligned representation, which, if you go far enough, could allow you, in principle, to train what I call like a sensor LLM, which is a system where you have this alignment in the space of sensors and of video and of language, and you could just query everything. Of course, the problem is that the effort for generating that is huge. And also, as I said before, you're talking about a very, very heterogeneous input space, which means, what do you mean by training a sensor model? Is it IMUs? Is it IMUs on your arm? Is it impedance sensor? A lot of stuff. What do you actually train? So we have been looking for ways of using that correspondence with a bit less of training. And here is where we come from, where the idea comes from. So it's something that originally had nothing to do with foundational models. We are thinking about the notion, imagine that you have sort of two sensors. One of them is more informative. For example, you're looking at doing dumbbells, right? You're putting something, so you have one sensor here and one sensor on the leg. Can I do something like training the system with both sensors and then using it for inference with just one of the sensors? It's something that goes a bit against the conventional wisdom of machine learning, right? Use the system in the same configuration you train it with. But if you go the way of essentially taking the sensors and training the sensors to generate sort of this embedding, this latent space, just like the language models do, right? So you train them on both sensors, you generate for each sensor its own embedding space, and then you use contrastive learning to essentially align those spaces. So what you are doing by that is essentially leveraging the fact that we're training the embedding space for the sensor with less information. It's an underdetermined problem. You have a lot of freedom how to train that space, right? You train many times with different initialization. You get good versions, you get bad versions. And you use the constraint introduced by the other sensor that knows more to enforce the creation of a version of this space that actually is better due to this knowledge. So essentially, we then use only one sensor to recognize it, and because we use the knowledge from the other sensor to structure that embedding space, we actually get a much better performance. So something that you see here is, if you use here only the target sensor without pre-training, you get like 0.52 accuracy, as compared to something like 0.7 if you trained on and recognized on both sensors. But if you go and use this pre-training method, where you use the better sensor to sort of condition the worst one, you get like 10% more accuracy, right? Which is actually quite, which is actually quite good. So which is the point as this one out, right? So you get this, it's actually quite a good thing by leveraging that information. So how does it relate to, and you can do that with different other sensors. So how does it relate to foundational model? So what we did is the following. We then started with YouTube videos, and we essentially used this motion to translate those videos into sensor data, but also to translate them into pose data. And then we trained an encoder for each of those modalities, as well as the language description of the actual activity. And where you use them to train this embedding, this latent space that you later use just for sensor-based recognition, right? So essentially, you use this embedding information from the world model contained in what you had trained here with this video and text encoder to condition your space where you put your, when you put your IMU data. You get, again, a significantly better performance. Especially, you get a better performance with little training data. Like when you use 2% training data only, the performance on the baseline is very poor here. However, if you use this preconditioning, you can get it into reasonable levels, right? So what you do is you use the information contained in the world model, contained in the foundational model, together with the ability to use this video to sensor translation to align slightly the embedding spaces to really benefit your recognition without training this entire sensor world model, right? So there's some more results we need to go through. Now, one of the problem of the generation of training sort of this data-driven models of IMU from video is that they tend to be noisy and not very good. So the next thing that we did, and I did something that for me is a very important way of using foundational models together with sensors, is that you go through simulations, right? So what I can do pretty well is I can take a video and I can generate from it some sort of a 3D model. Now these things are really good of a person or whatever is happening here, of the motion. And then if I want to do sensor data, then sensor data's relation to this 3D model is just physics, right? So I can go and use blenders and simulation to generate really good sensor data. And I can generate it for a variety of things. And now I have the possibility of actually creating a lot of data where video and language and alignment to this world model contained in the foundational model is now connected to my sensor data that I can leverage to condition my embedding spaces or to actually do my queries, right? And here's an example. So this is an input of raw data for a set of an open packets, an activity recognition data set. And if you do like supervised training, you see, you get a slightly better projection. But if you do this conditioning using the relation to the foundational model, you can actually achieve a much better structuring of your embedding space. And that notion of using simulation is something that, of course, opens a way to connecting more sensing realities again to this broad world model, right? So what we have here is a similar thing. We start with videos. We generate volumetric and sort of pose-based models. And the type of sensor data that we want to have is essentially pressure sensor matrix. So it's something you put on the ground, and it registers essentially as sort of an image, the pressure of your feet. is an extremely interesting sensing modality taken together with emotion, because if you think about it, what you do is very much related to the pressure you put on the ground, right? It's basic physics. Whatever you do relates to somehow pressing on the surface. Right? So it's a really good sensing modality. Difficult to get data on it, right? People can wear accelerometers, but we cannot have them always walking on the carpet, right? So, but then by being able to generate this simulation data, you can actually again connect it to this world model that you have, and by connecting to this world model, you can get data. So here you can see data for different activities, and you can see that's the ground truth. And that is sort of the type of data that you get through our simulation, but it's actually pretty good. Going a step further, the interesting way of using these language models for sensor data processing is that you can go and try to generate your training data from textual descriptions. Right? Because what happens is you have a model, I can talk to jumping jacks. The model can actually do a description of what jumping jacks are. There's a lot of work now of turning such descriptions into motion models. This is actually based also on GPT. And then you can do volumetric model, and then you can use your physical simulation to generate arbitrary sensor data. And again, this connection of foundational models and physical simulation is a very powerful tool of then connecting, allowing your sensor-based recognition to leverage the information contained in the foundational models, right? So here's again the result of what we are doing. So you talk about, say, walk back. The LLM sort of resolves it, and here's another sit, right? Resolves into more detailed description, and then the system generates a series of frames for the pressure metrics to actually be able to do that. Which then brings me to another important aspect of using these LLMs. You do not necessarily need to align your embedding for the thing to be useful. Because one thing that you can do is, if you talk about recognizing complex situations, situational awareness, what the model can do is essentially decompose your high-level description that you're looking at into arbitrarily detailed description of what does that mean, possibly down to physical signals, right? And once I can get the description, I can reduce the complexity of my recognition of my monitoring task into sort of the recognition of those basic components, which I then just have to combine using the information contained in the model. So again, I avoid this notion of training joint sensor and language model, but I can still leverage here the information that is contained there. So here's another example of similar work. One thing that we have been looking at recently is when I started working in the sensor processing, the way you would do recognition like in vision would be you would sit down and you would do some really, really elaborate feature engineering, right? For everything you want to recognize, you would compute the features, and then you would do the recognition. Then came deep learning, and everybody forgot about feature engineering, which has its advantages. You can recognize everything, which has a disadvantage that most of the students have absolutely no clue what the system is doing. Right? You just take the bigger possible network, apply it to the sensor signal. You ask them, do you understand what the sensors provide to them? Nobody knows, which is not a good thing. But anyway, and then the idea is to come back to it, to say, yes, of course, what the network learns is very good, but maybe we can use the physical features that you used to do before to somehow fuse it with what the network does to improve the performance. And it turned out that actually, that is exactly what happens. You can improve the performance. Not so surprising, again, we used to work only with the feature engineering, and for any single simple recognition process, it remains better, right? You have a simple recognition using sensors, you understand the physics of the sensor signal, you will always beat any neural network on a constrained task. The problem is, of course, that with this deep learning thing, you can have a system that can recognize and learn thousands of classes, and you cannot do feature engineering for every one of them. And that is where, again, this foundational model comes into place. Because what you can do now is, no, I cannot go on and for those zillions of situations I would like to recognize, formulate this feature engineering. But maybe I can build a system that has some sort of a physical model I can input into it, and then uses the world model contained actually in the LLM to do this feature engineering for me, right? To do not just this data-driven engineering, but with some input from me, from some knowledge graph or something, from some physics equation, actually decompose the activity into basic features. Right? Things like, you've been into sensor-based human activity recognition, what this thing does is recognizing you walking, you're sitting, you're running, right? You very often see people now taking huge transformer networks to take an accelerometer signal and recognize sitting from walking upstairs. Which is totally absurd, right? Because if you're just sitting, then you look at a vertical component, you look at the RMS, and you know you're sitting. You look at walking, you have the sinusoidal 1 to 2 hertz frequency, and it works, right? But of course, it doesn't work for everything. But if I can use the LLM to generate me such statement, like sitting means, you know, the leg is horizontal, low RMS. Running means this and that. Then I can actually automate this feature engineering. And I can also go a bit further. I can use that for things like, for example, pretext learning. So just to finish, here's another thing we have been doing with representation was trying to make those systems a bit less person-dependent, right? So again, sensor activity recognition on people. So essentially feature extractor, and then you would try to force the system to learn a representation that minimizes the loss in terms of similarity between different people, right? I would like the same activities done by different people to be farther apart. And then again, it works pretty well. But again, something that doesn't always scale. But the interesting question is, can I use the world model I have in the LLM to have the system suggest for me, for example, things like contrastive learning objectives? Can I use it to not just suggest the contrastive learning objectives, but can I use this to write for me the code that will compute those objectives, right? Then what I can do is sort of very much like, you know, you put an image to an LLM and you get a description. I can go and tell the system, I would like to recognize a set of situations where that involve, I don't know, doing some sort of sports or cooking or whatever. And then the system goes, queries the world model, and generates me the set of contrastive objectives and possibly pretext tasks that I need for pre-training that can actually help the system prepare for it, right? So again, no need to train the Jane model, but you can actually very nicely generate those things. So coming to the next thing we want to do in conclusion, despite that, we are actually now working on not building a joint model. However, we want to build a constraint model just for motion-based activities. And the idea is, and that's another thing where I believe using this model for sensor-based recognition is interesting, you don't really want to build a very general model of all the sensing modalities and that constrained to all the language information. But if you build smaller constrained things, for example, like something that related to human motion, if you build something where you actually can work a lot with physical constraints for your contrastive objectives, then that is something that can be pretty doable. So, coming to the end, what did I try to tell you, right? So the first thing is that if you look at this generative AI large language models, I believe, no, they cannot reason, they do not really can retrieve knowledge, they're just probabilistic distributions of lexical tokens. But they are fantastic world models, noisy, but absurdly comprehensive. And that means that they can essentially transform visual perception because they have this interface through the embedding to connect them to different modalities. And they can also facilitate the transition from perception to really situational awareness, again, by coming back to this world model. The second point was that really this latent space representation is really the core aspect. It reduces the complexity of our world to several hundred dimensional vectors, which is sort of mind-boggling. And then once it's been reduced, you can of course access, because I can map anything into a vector, right? There is a beautiful interface to connecting this world model to essentially anything. However, it's not always trivial, and as I've shown you, connecting it to multimodal perception has been pretty difficult so far, and little impact, because of things like heterogeneity of the input, lack of synchronized data, different information structures. Now, things that you can do as a solution, essentially, is first of all, this connection to synthetic data and also to simulations. Right? When you go into processing sensor signals, a lot of it is connected to physics, and then when you use simulation, you can create aligned data, you can create partially aligned spaces. And the interesting thing is also, it's not always about creating a model or an aligned data space, but very often you can use these language models and the world model context in it to essentially link high and low level context. and to generate and configure your training process, right? So rather than having a system where you go and input a sensor scene and get a description, you can provide textual video description of the type of activities that you want to recognize, and the system is likely to provide you with a configuration, with something that you can do to very quickly train, or even with a pre-trained system that you can then use to actually do your recognition, right? And that is something that can be done on a specific hardware, that can be done in low power, which sort of is the link to things like neuromorphic computing. Actually, I have quite some activity on low power implementation of those things, and this notion of having this thing running on embedded devices is a motivation for much of the work on this alignment of embedding spaces that we have been doing. Thank you.
Okay, thanks a lot for your presentation, for being so on time. So therefore, we have a lot of time for questions.
No questions.
People. Yeah. Then, while people are thinking about questions, let me ask a question concerning the last point with the hardware. So, what would be needed in terms of hardware to do this kind of implementation of your models? So, what are the requirements?
So what we have been trying to do is to see how you can essentially take this very high dimensional space, this embedding that you have, right, and to project it to a low dimensional embedding with a representation that you can then implement more reliably in the hardware. The other thing that we have been doing is to see how you can take the encoders, right, because it's all about encoders. At the end, you reduce the whole thing into building encoders, and those encoders then, once you know the structure of your embedding, you can simply build them in hardware much more efficiently. So one thing we're trying to do is always to go and find this optimal point between optimizing the architecture of your network, optimizing your hardware, right? So I have my group of hardware people and machine learning people, and they usually fight about how to do that, and the result is usually the best system.
Okay. Yeah, so my idea was about that associative memories would be a good solution, right?
That could probably help, yeah? It's a good idea. Yeah, so we have a project, we work like with one of the companies that do like processing in memory, for example. Right? That's another thing that seems to work pretty well.
Okay, so now questions.
I think everybody wants to go to the next session. So.
Yeah, that's
maybe one quick question
okay.
here. Jan from Forschungszentrum Jülich. So far I understood that one big challenge is the missing data aspect of different modalities. Are there also more challenges? I can imagine that so for vision and language I can see that probably information content is very aligned, but with different modalities you might have different or less information, so fully aligning the representations is maybe not possible. So are there further tricks that are needed or further architectural changes or something?
So that was one of the points I was trying to make in the last part, that we didn't actually go and try to train a new model, right? You take synthetic data, you train a model just like a vision language model, use a sensor language model. I have my doubts whether it works, because as I said, and you also said, the nature of the information is different. So you'll be aligning things that don't work. But what you do instead is this notion of taking a constrained sensing problem and then trying to somehow condition the structure of the latent representation that you generate through sensors with the structure of the embedding that you have from language. Right? So it's not hard forcing it, but you're using that information, and that really seems to be helping. That is what we are doing in many of those applications. Is rather than forcing it to have a single embedding space of things that don't belong together, trying to extract this piece of information that actually helped me structure it better.
I see. Thanks.
okay. So I don't see. There's a question, right?
Hello, thanks for the talk. I'm Douwe den Blanken from TU Delft, and I have a question. So you have a lot of models that you discussed. So are these open? Can we use them to generate embeddings to train smaller models or to do different downstream tasks?
So those things I was presenting are essential papers. Some of them are actually really new work. We just submit that. Most of the thing, if you're interested, you can let us know. It's nothing that is like being made open, like GPT. You know, it's essentially experimental code, right? But some of the things, yeah, you just let me, we're happy to share those models for people to work with.
Okay, sounds good. Thanks.
Okay, so then let's thank the speaker again.